So I'm going to be talking about fine-tuning large ASR models for accurate speech recognition for low-resource languages. So a bit of a background for this project. It came about, there are two projects that are kind of linking up, and it's looking at ways in which we can provide smallholder farmers with accurate weather data and agro-advisory related to weather forecast. So smallholder farmers in Kenya, majority, they are like a third of the country's food comes from smallholder farmers. Smallholder farmers are defined as farmers who farm on less than 3 acres, and they are quite, despite them being basically our food basket, they are very under-resourced compared to large-scale farmers. And so what we wanted to see is, can we give them accurate weather data that is localized? So a lot of them rely on regional weather forecasts that are delivered through the news or the radio station. So you know your usual weather station forecast, it gives you like a regional outlook. But then that's not very specific to their location, because we have very wide different terrains. And so it could, what they normally say, it can be raining down in a ward X, but over here it's not raining. And so they need localized information. So the project, one aspect of the project is looking at building smart weather stations. And so we want to deploy weather stations to different farmer groups. And so we have farmer groups at a specific ward or cutting across different wards. So wards are like the smallest granular level of a location in Kenya. So we have counties, and then within counties we have sub-counties, and then within sub-counties we have wards. So if we can get localized weather forecasts at the ward level to the farmers, but then now we have to start thinking, how do we give them the data in a way that makes sense to them? So you can give them the weather forecast, tell them that it's not going to rain today, but then what are they going to do with that information? So you have to give them agro advisories that are linked to the weather. So you tell them it's not going to rain today. You can think of starting to mulch, or you can think of starting to irrigate. And here are the sources if you want to set up an irrigation scheme, or a like cheap irrigation or drip irrigation, and give them that sort of resources. So that's the whole idea. But we found out a lot of our farmers are digitized. So they do have a mobile phone, whether it's a feature phone or a smartphone. But not all of them are able to access information either through low digital literacy, or just they don't speak English. So a lot of our information online is in English. So not a majority can read English, and not a majority speak English. So Swahili is our national language. Majority speak Swahili at the baseline. So you expect someone to have, if you've gone through formal education to some level, you speak Swahili. And so that's where the project came in. Can we build voice bots for smallholder farmers? So what we like to call it a Siri for Swahili-speaking smallholder farmers, where they can query a plant that they're interested in farming, and they're able to get the information back to them in Swahili. So you're able to interact with it much easier through a simple interface. So this part, we realized there are not a lot of ASR models that have been fine-tuned to Swahili language. It's a low-resource language. I wouldn't call it low-resource anymore, because then, as you'll see in the presentation, there are a lot of resources nowadays that can help us build ASR models for Swahili. But it's still there. And then Swahili is spoken by more than 80 million people in Africa. And so we don't have a lot of speech technology that's open source. Google does a good job, but you have to pay for their ASR models. So we want to open source models that anyone can plug into whatever farmer-facing application that they want to build. So we see automatic speech recognition as a bridge to build a digital divide for settings with low literacy and low digital skills. So what ASR allows is ease of access to information. So you don't have to learn how to read. You don't have to necessarily read. You can just query a knowledge base using voice in your the language you're comfortable speaking. And so you're able to interact with technology easier and obtain the information they need. So currently, if you want agro-advisory information, you have to go to a website in Calro, click a couple of buttons, and then you get like a huge transcript of what you're expected to do. Some farmer-facing organizations send SMSs, so they try to digest that content into bite-sized information via SMS, but we realize that SMS will alienate people who can't read. And so providing an interface that has voice-enabled technology kind of bridges that digital divide. Again, it simplifies users' interfaces, eliminating the need for complex navigation or typing. So you just have like a Siri or a Google AI sort of voice-activated interface to access the information. And then it increases independence when interact with the technology, so you can, despite your level of technological digital literacy, you can perform tasks, access information, and without relying on others. So a lot of people who can't navigate technology have to rely. So our smallholder farmers, majority are above 60 years, and so they rely on the younger generation to kind of navigate technology. And so basically we see it as a way to empower individuals to access digital resources. So what happens? So contemporary ASR models need large quantities of labeled data for each language. Swahili, at the moment, there's a lot of work trying to build it, but it's not there for a lot of languages that are what are called low resource languages. So there's data scarcity, there's lack of sufficient amounts of annotated speech data. So you need speech data that is annotated, and there isn't a lot of that. There's also limited text resources. So not a lot of text resources that can be transferred to speech and then kind of use that to generate speech. Another issue is around computing resources. So dedicated GPUs is a limited resource. Whether or not have access to cloud computing. I don't know if everyone has ever interacted with cloud products like Google or AWS. Getting a dedicated GPU is not always assured. You have to send requests to the sales team. The sales team has to review your request to see if it's sufficient enough, even if you're going to pay. And then you have to wait for you to get assigned. And once you get assigned, it's not assured the longevity in terms of how long you have the dedicated GPU. And then there's a lot of specialized setting up cloud computing environments. So I think AWS and Google, they don't make it very easy to set up cloud resources. So you need sort of a cloud engineer to kind of, it's not like a plug and play solution. So you need a lot of resources in terms of that. So for low resource language, you have this double bind sort of problem in terms of data and computing resources. And so in terms of data, we have now what we call Mozilla Common Voice dataset. And so what the Common Voice, Mozilla Foundation has this project called Common Voice. And what it tries to liberate access to voice datasets. And how does it work? You go on to Common Voice. You could either contribute your voice. So if I'm a Swahili speaker, I can go in. They have sentences in Swahili, and I just read them out. And then you can do that. You get like 5 tries per day, so you can do that continuously. The other way it works is to get writers to contribute their sentences, because there are issues around, if you can't just take a book, break it down into sentences, because there are issues around copyright. And so they do continuously seek writers, teachers to contribute sentences that can be used to collect their voices. I think now they wanted to try and experiment with ChatGPT to generate sentences, but there are issues around getting context for different languages. So ChatGPT does a direct translation from English to Swahili, so it kind of loses context, Swahili context in words. So it's normally not a direct translation. And then you have speech validation. So you go on there as a volunteer and you're able to validate the speech samples that have been given, whether they are clear, whether they are accurate, whether they match the sentence that was meant to be read. And then if you feel your language is under-resourced, you can request for your language to start getting collected, and then you create like a community around that. And then they are quite forward around gender-aware contribution. So there's a push to, there's research showing that speech recognition technologies kind of don't perform as well for female voices, because the data on female voices and minority groups are very little. And so there's a push towards having this equality in terms of the data and reducing the bias. And so for Swahili data, we have now about 929 hours, so that's quite a lot. 38% of that have been validated, so it's gone through a validation process from around 1,163 speakers. So it mitigates bias in AI by democratizing speech tech for everyone. So it lowers the cost of collecting this type of data through crowdsourcing. It's open source and free for use, and they have a gender action plan for more inclusivity. And so that's, in terms of the data, that's kind of the solution that's going around. Swahili, I think the Swahili data source is about 2 years old now. The biggest one in terms of African languages is Kenya-Rwanda, which has about maybe 4,000 or odd hours. So that's fine. So we have the data now. But what about the models and the computing resources? And so we have what we call pre-trained ASR models. So these are models that have been already built using high-resource languages, so languages with a lot of data already collected, but they're already pre-built, and so they've already kind of used the computing resources to pre-build to recognize speech. And so they already have the hours of label. So what you do is you pre-train a language model on a large data set and then fine-tune it on a smaller label data set. So in these categories, there are two of them. So you have unsupervised models. I quote unsupervised because they use unlabeled data, but use a self-supervised learning technique to be able to learn the language, the speech modeling from the large data set. So you don't need a labeled data set. So the methodology or the tool that has come out, the model that's come out of this is the WAV2VEC model by Facebook. So what they did is, training speech recognition takes a couple of steps. So you do the feature extraction, whereby you learn the voice features, analyze it using spectrograms, and then now you do the acoustic modeling, whereby you put in a model that learns how the speech varies. And then now you do the language modelings that matches the speech to text and does the transcription, and then you do the decoding, which now transforms the speech into text. And so what WAV2VEC was able to achieve is that it's able to learn the local language patterns by masking different aspects and then predicting that on a new data set. And so what they say is once you train a large model like WAV2VEC on a large data, you're able to fine-tune it on a smaller data set, on a smaller labeled data set. So you have a transfer learning sort of thing whereby you're able to transfer the recognition of an unlabeled data set to a smaller labeled data set. And then we have now supervised models like NVIDIA NeMo, which is a toolkit. It has different models that have been used to, that have been trained on large language labeled data set, and then you're able to fine tune it on a smaller data set. More recently, we have Whisper from OpenAI. It was trained on around 6,800 hours of a multilingual data set. So that one is the most diverse sort of model because it's not just able to do the transcription, but it's also able to detect speech. And so what pre-trained large language models are able to afford us is that it offers, it lowers the amount of labeled and unlabeled data to build the speech recognition system. So basically it removes the challenge around computing power. And so we have different research that has shown that with just a small data set, so Betsy was able to train a 10 minutes labeled data. I think they were using the Libri speech. So with just 10 minutes, you're able to achieve a word error rate of 5.2 per 100 words on a downsample Libri speech data set. For a low resource language, like the Japung language, it's a small language in China, they were able to train on just 10 hours of labeled data and achieve a word error rate of 18.5%, which is great. And then much closer to home, we have Elamin, who fine-tuned a NEMO model on Kenya-Rwanda language, and were able to achieve various improvements. So what we see here is that by using pre-trained large language models, we are able to fine-tune that on a smaller data set, and then have use transfer learning to get those benefits. And so what our experiment wanted to look at is, can we even lower the amount of computational power needed? The Elamin paper used Swahili data. They had about 48 hours, but you still need a lot of GPU processing power to kind of analyze that data. So the question was, can we use free resources from Google Colab? They give you a GPU of about 12 GB, 100 compute units. Can we use that to be able to use the already pre-trained language models and get that advantage? And so the data we used was 5 hours of Mozilla monolingual Swahili data set. We broke it down between female and male, so we have about 3.3 female and 0.8 male hours, both train and test. So we do have a large proportion of female voice speakers. So to train 5 hours, maybe I'll put a disclaimer, we had to actually upgrade our Google Colab resources, only because the maximum you can do with the free version is about 1 hour, and the gains from the gains are very marginal. So let's upgrade to 100 compute units and double the amount of RAM that's already given by Google Colab. And so nowadays you can subscribe to pro versions of Google Colab, and they give you like a dedicated, well, not dedicated, but they give you some good GPU. So we used 5 hours of data. And then the model we wanted to look at is a smaller version of Whisper. So it requires about 2 GB of RAM. And then we also tested the WAV2VEC. We didn't test NEMO because NEMO still needs a lot of computing power to run. And then the evaluation, we stuck with the word error rate, which looks at the number of words gotten wrong from a reference model. So data processing, we went through the usual data processing, data standardization, removing punctuation marks, etc. Mozilla Common Voice is recorded in MP3, so you have to convert to WAV formats. And then convert the audio to log-mel spectrograms for the model. And then we use Whisper Tokenizer to tokenize the text input. So basically tokenizing is just breaking the text input into like the common, vocabulary words, yeah. So what we found out is that with Whisper Small, we are able to improve our performance from the base model by fine-tuning on our sample data set. So the word error rate achieved using the flows data set was about 0.73 or 73%. We're able to bring it down to 45%. And this is just 5 hours of training data. The flows data set had about 30 hours of Swahili training data. And then for WAV2VEC, it was interesting. We actually had bad performance. So the devoice data set had achieved a word error rate of 0.23, but we got a word error rate of 0.64. This could be because it's an unsupervised or self-learning method, so probably it needs more data than 5 hours. And so it probably performed worse than Whisper AI because of that. We're still trying to figure out why it didn't perform as well. So yeah, so that shows us that, well, you can achieve the pre-trained ASR models gives you advantages in terms of being able to just train on a small data set. You don't need as much resources as you would need if you're training from scratch. And then what we now want to do is look at, okay, fine, we can do that. It's performing well on a base purely Swahili. So a lot of Kenyan speakers specifically don't speak fluent Swahili. A lot of us are multilingual, so when we are speaking informally, we code switch between two languages. Majority would code switch between English and Swahili. And if you go even further into the rural areas, you code switch between Swahili and your mother tongue. So there's still a lot of work being done. So this I tested on the NEMO model, the NEMO Swahili model. So the previous research had a multilingual data set of Luganda, Kinyarwanda, and Swahili, and then it achieved like a 12% word error rate on Swahili. So it's pretty good in recognizing Swahili. But if you code switch between Swahili and English, it doesn't recognize the English as well. So the example there, I gave it input as, so a lot of these models are already on Hugging Face, so you can go out and test them. So I gave it input around, the sentence is, ningependa kujua kuhusu tomatoes. So you'd expect a lot of people to speak that way because some plant names remain like soya beans. You wouldn't know the direct translation in Swahili unless you live in Tanzania because they speak more fluent Swahili than Kenyans. So yes, so the input is I'd like to know about tomatoes. So the tomatoes part is in English, and so it's not able to transcribe the English part very well. So what we want to go now and train is, can we build a multilingual data set? So the first idea we have is that we can get a purely Swahili data set and an English data set, combine that, come up with a multilingual data set, and then fine-tune a model. But a more interesting way, because fine, you can combine the two, but you don't get the context in which how we switch between different languages, because there's a pattern to it. And so if you have a purely Swahili and a purely English, it won't get the context. So what we want to do is, can we get Kenyan rap audio? And so Kenyan rap, normally, so rap because you can get the speech, you can easily dissect the words. But Kenyan rap because there's a lot of code switching, and even more code switching than how you'd normally talk, because then you have English, you have Sheng, which is Kenyan slang, and then you have Swahili. So it's a mix, it's an easy way of getting code switch data rather than just doing the data collection from scratch, or having people read text inputs and then collecting that data. So Kenyan rap would reduce the effort that you'll need to do that collection. So, but then there will be issues around copyright and all that, so we need to figure out how to do that, because you just can't go download audio from YouTube. And then Swahili dialects. So the project is funding different groups. So if the Congolese have been having trouble because Congolese people speak Swahili, but it's a different version of Swahili, different from what Tanzania and English speak. So theirs is mixed with, because they are a French-speaking group, so the L sometimes is an R. The words are different. They are mixed in with their own mother tongue, and they're different. So they have a very different Swahili dialects, and the further away you get from East Africa, the more diverse Swahili gets. And so how do we kind of get and train for different Swahili dialects? So that's a question. And then even further down is looking at regional languages. So Kenya has about 47 tribes, and each of the 47 tribes have their own language. And so if you're looking at targeting rural farmers, their language of the one they're comfortable with is more likely their mother tongue or their regional language. And then if you now look at East Africa, it gets even more diverse. So how do we capture our regional languages? And then what you're finding is as we get more urbanized, the more we lose our mother tongues. And so, for instance, I'm Kikuyu, but I don't speak my mother tongue because my mother never taught me, but anyway. So how do we capture even further to be able to capture different diverse sources and enable us to communicate with technology in the language that we are most comfortable in. So so that's my presentation, some acknowledgements on the funders and some references. So thank you. Yeah.
I'm really interested in this idea of lowering barriers to participation in the digital world. And it strikes me you have some really thorny issues to deal with some of these languages. I love the idea of using rap. I mean, could you record radio? There's radio copyrights in the same.
Yes. So you'd have to get permission from the radio broadcast. Just because it's broadcasted widely, you still have to get permission. So there are people, so Mozilla has been trying to work out the thorny issues with copyrights, especially around text and audio. So so there's still a lot of copyright. Media houses are normally, they see it's mine, and so they're not willing to share. So we are thinking if we can get rap artists to donate their audio, and even if it's studio audio, even the better. We can do like try to make it cool, and then maybe the rest will follow. Yeah.
Thank you, it was really interesting. I was wondering about the same sort of issue around trying to collect data, particularly about these sort of code switching and dialectal sort of sides of Swahili. Is there any opportunity for you to be collecting speech data from the audience that you're intending this for in the end, from the farmers and the people out in the rural communities? Or is that too expensive to be going out and speaking to everyone and collecting that data?
Yeah, so we did collect like a validation data set. So we had the farmers, when we were doing like our baseline survey, read a couple of sentences, and then we collected that way. But yes, it would be quite it would need like a separate project to just go out in the rural areas and get all these people to donate their voices. So Mozilla, again, it's a platform. You need the internet. You need to join in, log in, and then donate, read the sentences. But yeah, it will be interesting to get like. I think it's something that they might think of funding if you give them like a proposal. So we just didn't have the time because we had so many other so we have like a small validation data set to validate the different models, which we haven't done yet. So I think we'll do that soon. Yeah.
Okay, great. Let's move on. If there are any more questions, let's be here at lunchtime. Will you still be? Yeah. So let's continue the conversation over lunch. Thank you so much, Betsy. That's great.